Hi guys, welcome to my second episode of Love the Byte series. My name is Samuel Kamochu, a telecoms and a software engineer. I'm a co-founder and the lead paysetter at Meliora Technologies. In this video, my focus will be to get you comfortable with the relevant computer number systems, that is decimal, binary, hexadecimal, and even octal. So what are these number systems that you're calling the relevant? So you already know the decimal. The computers don't use decimal number systems, but we think in those number systems. It has symbols from 0 to 9. Binary has only 2 symbols, 0 and 1. Octal has 8 symbols, 0 to 7. Hexadecimal has 16 symbols, 0 to 9. Then from 9, instead of counting to 10, we use A as a symbol. 11 is represented as B. 12 is C, D, E, F, and F is essentially equivalent to 15. So, but before we move further, allow me to just take you back to a very basic concept of counting. So we know that in decimal, when you count 1, 2, 3, up to 9, the next value must be represented with 2 symbols. And in this case, we move to 1, 0, or what we call 10, meaning that we have a full set of 10, but we carry forward and represent it to the left. So then from 10, we move all the way from 11, 12, up to 19. Now, once we get to 19, we get to the same problem. We have to, the next value, there is no symbol to represent it. So we have 9. When you take it to 10, it becomes a full set of 10. Now we have 2 sets of 10, which we represent as 2, 0, or what we normally refer to as 20. In the same thinking, hexadecimal, we count from 0 to 9. But once we get to 9, we move to A, B, C, up to F. Once you get to F, we are out of symbols. So we have to use now 2 symbols to represent. But now the next value from 15 is a whole set of 16, which we just represent as a set of 16 values, and then together with a 0. So please note the number on the left has more value, which is 1. And we say that the place value of 1 is 16. So then we move from 1, 1 up to 1F, which is the maximum symbol. And once we get to 1F, the next value will take the F now to another set of 16. Now we'll have 2 sets of 16s, and that will be represented as 2, 0. Please note, it's 2, 0, not 20. 20 is a value within the decimal number system. So now we move to binary, which might be a bit complicated. So we have 0 to 1. So once we get to 1, we don't have any other symbol. We have to represent the next value, which is 2, as 2 symbols. So we'll represent it as 1, 0, which means that we have a set of 2 values and a 0. So the place value of the digit on the left is actually 2. And move to 11, and of course from 11, some of you might guess, from 11, if you add 1 more value, you essentially get 1, 0, 0. Now move on to the place values. So we have a number like 356 or 356. We know that the 6, the place value is 1s, then 5 is 10s, and 3 is 100s, or 10 to the power 2. Similar concept, we move to base 2. So we have, this is 1s, 2s, which is 2 to the power 1, and then 4s, which is 2 to the power 2. Base 16, we use the same concept. 1s, then 2 is 16s, or 16 to the power 1s, and A is 16 squared, which is 256. So now we move on to the computations, now that you know the place values. So we'll look at 17 plus 6. We already know how to do that in decimal. So we take 7 plus 6, becomes 13. 13, we represent 3 there, and we carry 1. Once we carry 1, 1 plus 1 becomes 2, and we represent it as 2. Alternatively, we can use a generic method where we take 7 plus 6, becomes 13. Then the 13 is not a number, that is a symbol within the decimal. So what you're going to do is you're going to divide by the base, and then you have 1 remainder 3. So what you're going to write is a 3, then we carry 1. Once we carry 1, the rest continues. Using the same concept, let's look at the base 16 computation. So you add A. So we know that F is equivalent to 15, A is equivalent to 10. So we have F plus A is equivalent to 15 plus 10, which gives us 25. 25 is not a value within the base 16. So what you're going to do is we divide by 16 and we get 1 remainder 9. Now we write 9 and carry 1. So we write 9 and carry 1. Once we carry 1, we have 1 plus 9, which is equivalent to 10. But 10 is not a value in, it's actually a valid, there is a symbol for 10, which is A. So we're going to write A9. So 9F plus A is the same as A9 in hexadecimal. Similarly, we can do binary computation. We take 1 plus 1, 1 plus 1. At least you know the answer from the previous slide. So what you're going to do is we'll do 1 plus 1, which gives us 2. 2 is not a symbol within the base 2. So what you're going to do is we divide by 2 and we get 1 remainder 0. So we do 0, then we carry 1. So we write 0, then we carry 1. Once we carry 1, we add it to the other one that we have on the second place value, which gives us 2. Remember, 2 is equivalent to 1 remainder 0. And then what we do is we write 0 and then we carry 1. The one that we've carried, we add it to nothing because we don't have anything on the that place value. And we're going to get 1. We write 1 and finally we know that 1, 1 plus 1 is equivalent to 1, 0, 0. So let's look at how to convert these numbers from octo to decimal. So let's look at a number called octo to decimal. Here we apply the place value concept. We know 5 is ones, 2 8s, and 1 64s. So we just multiply each of the digits times the place value, and we get 85. We know that 125 is equivalent to 85 to base 10. So let's move on to base 2 computation, and we take ones, then we take twos, take fours, and we take eights. So we know that we have 1 8s, 1 4s, 0 2s, 1 1s. So if you multiply that, you get 13, and we know that 1 1 0 1 is equivalent to 1 3 in base 10. So finally, we look at base 16, and we know C is 16 to the power 0 or ones, A is 16 to the power 1, which is 16s, and 1 is 16 to the power 2, which is 256. So similarly, we know that A is 10, C is 12. So we say 1 times 256, 10 times 16 plus 12 times 1. And that gives us 428, and we know that 1 AC is equivalent to 428. Now that you know to convert any number system to decimal, let's look at converting from decimal to any of the number systems. So we'll use the same values that we looked at in the previous slide. So we have 85 to base 10. We already know that it is 1 to 5. But how do we convert back to decimal? Sorry, to base 8. So we take the 85, we do the division now. We divide by 8 and we get 10 remainder 5. So we write the 5 and we mark the remainder because the remainder will give us the final answer. So we take the 10, we divide by 8 again, and we get 1, which is remainder 2. So we write 1, then 2, then we take the remainder down there. So 1 divided by 8 gives us 0, remainder 1, and we take 1 to 5. And the answer is 8 5 to base 10 is equivalent to 1 to 5 to base 8. So let's look at base 2. Similarly, we will take 13 divided by 2, which is the base, which is 6, remainder 1. And we'll also record the 1. Then we take 6 divided by 2, which you get 3, remainder 0. We record the 3, then we write 0 down there, which we record as the remainder. So we take 3 divided by 2, we get 1, remainder 1. So we essentially record the remainder. Then finally, the remaining 1 divided by 2, we get 0, remainder 1, and then we record the remainder. That way, we know that 13 to base 10 is equivalent to 1101 to base 2. So finally, let's look at base 16. And what you're going to do is we'll take 428 divided by 16, which will give us 26, remainder 12. Here we get a bit of complexity. 12, we know that 12 is the same as C in hexadecimal, so we represent it as C. And then we take 26 divided by 16, we get 1, which is 16, remainder 10. So we write the 10. 10 is also represented as A in hexadecimal, so we write A. Then 1 divided by 16, we get 0, remainder 1, and we take the remainder down there. And finally, we confirm that 428 to base 10 is equivalent to 1 AC. Now that you've done that, allow me to give you a few practice questions. So right now you can pause the video and do your computations, and come in and pause when you're ready. I hope you have done the computations, and I'll just show you the answers as displayed on the screen. Please note that 25 times 6, the operation was multiplication and not addition. 168 is A8, C0 is 192, and O0, please note there was a complexity. We were converting from base 16 hexadecimal to binary. So it's 1101. So some of you might be wondering, why are we covering these things? I'll give you one illustration. In the life of a software engineer, you might experience something called hexadecimal stream, or a hex stream or a dump. Normally, a stream will contain numbers as indicated above, but I want to do something interesting with you. Let's convert these numbers into decimal. So you know that C is 12 and the place value is 16. So 12 times 16, 192, plus 0 times 1, 192. So then we have A8, you can do the computations. A is 10, 10 times 16, that's 160, then plus 8, which gives us 168. 0, 1 is equivalent to 1 in decimal. And of course, 1, 1 is equivalent to 17, which is 1 times 16 plus the other one, which is ones, and you get 17. So if you look at that number, if I add the dots between each of the decimal value, then I have 192.168.1.17. This number looks familiar. Essentially, this is IP address in the version 4, IP Internet Protocol version 4. So I hope this helps. And if you found this session or this video interesting, or you believe that someone could benefit from the same content, please share and feel free to like, comment, and subscribe. Thank you so much, and see you again in the next